Welcome to this CMCC webinar. Before to introduce the speaker, just let me say a few words about CMCC, or at least this is the usual procedure. So CMCC is a leading research center focused on understanding the interaction between climate change and society. And our mission is to ensure and provide reliable, rigorous, and timely scientific results to stimulate sustainable growth, protect the environment, and develop science-driven adaptation and mitigation policies in a changing climate. CMCC is structured in three research institutes: Institute for Earth System Predictions, Institute for Climate Resilience, and the European Institute on Economics and the Environment. The climate science and social science researchers from all over the world collaborate in the multidisciplinary environment that these three institutes and the collaboration between these institutes ensure. Besides the institutes, the CMCC activity are also integrated through the strategic programs. In particular, we have three strategic programs, one on integration of the planetary biogeochemical and the industrial carbon cycle. And then there is another program on predicting socioeconomic impacts of climate change, so passing from prediction of climate conditions to prediction of socioeconomic impacts of these climatic conditions. And the third program is on global costs as a new frontier. As I said, these programs integrate the research activities performed across the different institutes. And since we are a modeling center, we also have a high-performance computing center. Here in this slides are reported the numbers of our computing facilities and capacities. As you know, CMCC is distributed institutions, so there are different premises across the countries, and here are highlighted the cities, the locations of our offices. Finally, this slide shows the member and the institutional partners of the foundations that, as you can see, are Italian, but not only Italian, research institutions and universities. Now, just 2 words about the question and answer session. So now we enter into the webinar domain. The QA session is organized as usual. Your audio and video are deactivated. I mean, I'm referring to those that are attending the webinar on remote. Audio and video are deactivated, and you can ask questions just using the QA button that you find on your screen. Now, let me introduce the speaker, Gabriel Vecchi. It's a really great pleasure for me to welcome and moderate this seminar by Gabriel Vecchi, who, in addition to being an old friend, is one of the most brilliant and authoritative climate scientists on the international stage. Gabriel got his PhD in physical oceanography at the University of Washington, and currently he is the Knox Taylor Professor of Geosciences at Princeton University. the director of the High Meadows Environmental Institute. And by the way, CMCC has recently established a partnership with this institute. And he's also deputy director of the Cooperative Institute for Modeling the Earth System at Princeton University. Gabriel is author of some of the most important and seminal papers exploring the dynamics of tropical circulation and the effects that climate change has on it. And currently his research focuses on the relationship between climate changes and extreme weather events, particularly hurricanes. And this more or less is also the topic of the webinar today, since Gabriel will illustrate and discuss what we know about the impact of climate change on the occurrence and dynamics of hurricanes. So without further delay, I leave the floor to Professor Gabriel Vecchi.
Oh, Silvio, thank you. And thank you all for taking time off of your busy schedules to join this webinar. I hope I've managed to share the slides successfully. So today, I'm going to go through a sort of summary of some work that we've been doing to really try to understand how to connect our understanding of what may happen in the future with hurricane activity with what has happened in the past. It's a very challenging exercise and involving exploring climate modeling, basic theory of tropical dynamics, and weather scale dynamics, as well as digging deep into observations and understanding what they mean. I'll use two general examples that are of importance in my opinion. One is looking at global tropical cyclone frequency, and then I will look at major hurricane frequency. And I'll touch at the end, hopefully, on a little more of some of the things that we really know confidently. So the first two topics will have a great deal of uncertainty connected to them. Of course, I'd love to thank my funding agencies. Without them, this would have been harder to do. But most of all, I'd like to thank all the colleagues that I've managed to work with. So in the United States, it's very easy to motivate understanding tropical cyclones. I think even in Italy, you see it in the news. Tropical cyclones are, from one sense, incredibly beautiful in some sense, geophysical phenomena, but they're incredibly devastating to society, to people's lives, ecosystems, the economy, when they impact land and society. Tropical cyclones depend on a feedback between winds, evaporation, and rainfall to sustain them, and therefore warm oceans, a moist atmosphere, and mild winds in the atmosphere are set the stage in which they're more likely to happen. The damages that we get from tropical cyclones tend to come from direct wind damage, both from the cyclone as well as tornadoes that tend to spawn at landfall, freshwater flooding from rain, and waves and storm surge. And here you can see some of the tragic losses that have happened in some historical cyclones. Tropical cyclones, here is an image of Hurricane Dorian from 2019. This is satellite data illustrated by Professor Kim Wood at Mississippi State University. And what you can see is the development of convection as the storm now is making its way over the Windward Islands in the Caribbean, and now it's going over U.S. Virgin Islands, passing by Puerto Rico, north of Hispaniola. Then you start seeing the development of a very clear rotation in the storm. The storm sort of organizes. It becomes this classic tropical cyclone with a well-developed eye. Here it's encountering the Bahamas, and what you will see is Hurricane Dorian park itself over the Bahamas here temporarily. It approaches Florida, but doesn't quite make landfall, stays over the Bahamas for a while. and then it moves eventually to the north and encounters high wind shear, interacts with land, and it becomes more asymmetric and typical of an extratropical cyclone, undergoes extratropical transition. What should be clear from this example is that tropical cyclones, they undergo many phases in their development. And although the very classic symmetric warm core, well-developed eye of a major hurricane is sort of the prototypical image of a tropical cyclone, there are multiple phases, and I'll come back to that later, where you cannot think of just a tropical cyclone as its mature stage, but you need to think about how it transitions over its life cycle. So a big question in hurricanes and climate is, what will the frequency of tropical cyclones do globally in response to projected global warming? A number of studies have asked this question, including some studies led by the CMCC. There's been some seminal work by Silvio, as well as by Enrico Scocimarro, and a few others asking this question, and it's been happening at a number of labs. And this figure on the left shows an exploration of all these studies put together in 2020. Led by Tom Knudsen, but involving people all around the world, where they collected all the results from the published literature. And what they find is that there's a great range of the response of global frequency to warming. This is the number of tropical cyclones everywhere on the world. And you see anything between a 30% decrease and a 25% increase over the in response to CO2 doubling, with the bulk of the modeling results showing a tendency for a decrease. However, this tendency for a decrease of about 20% of number of storms per year is not unanimous. There are some studies that suggest that there may be as much as a 20% increase in frequency. This is the 2020 result, but it's not a new result. If you go back to the first published study using a global climate model, here on the right, this is a table from Broccoli and Manabe in 1990. Showing the response of tropical cyclone frequency in two different versions of the Manabe coupled climate model. And what you see here highlighted in red and highlighted in blue are that this same low resolution climate model in 1990 shows that you could get anywhere between a 6% increase and a 6% decrease. So over the past 30 years as a global community, we were working really hard, and we managed to reduce the uncertainty from -6 to 6 to -30 to 30. Oh, wait, that's an increase. All right, so we broadened the uncertainty. We've mapped out the uncertainty. So it is a challenge to plan for a warming world when we don't know what hurricane frequency is going to do. So what we've tried to do is see, can we use observations, basic theory, to better understand why this spread in model projections is there, and can we reduce the spread? One of the approaches that we've been doing, and this has been really led by my colleague Sung-Lin Hsieh, where we've used a hierarchy of models to try and understand the processes that connect climate to genesis, the climate to the number of storms, in as a sort of general sense as possible, not constraining ourselves to understanding the world we live in, but trying to understand all reasonable worlds that are related to the world that we're living in. And so we'll explore everything from a realistic planet that has the continental configuration we live in and the ocean temperature structure that we have, to a water world, although we allow the tropics to be warmer, to a homogeneous water world where the planet is just a sphere but with uniform temperature, and exploring across these ranges of climates allows us to really build generalizable understanding that is hopefully also applicable to a future warmer world. So one of the results that we've found is here using 3 different GFDL models. These are models developed at the Geophysical Fluid Dynamics Lab, the NOAA lab here at Princeton. They differ, in their structure, they're much more similar to each other than any published, any other climate model. And we explore them in idealized contexts where we perturb 3 versions of these models, either with uniform CO2 increase, where we don't allow the ocean temperature to warm, or we prescribe uniform ocean warming, or we prescribe uniform ocean warming and CO2 increase. And these are sort of the most idealized and simple perturbations that we can make to a model to really understand what it does in a warmed world by increasing CO2. And these 3 versions of a model that are very, very similar to each other indicate a couple things to us. One, that there's a consistent decrease to the radiative forcing from CO2 independent of warming, but that in response to uniform warming, you can get anything between a 15% decrease to a 15% increase. And when you apply both warming and greenhouse gases, it's a very linear response. And here, with a family of models that are very, very closely related to each other, we're able to recover largely the spread that exists across models in the world. So these models now become an ideal laboratory in which to understand what drives this spread across different studies. One of the ways that that models or that observations and models have been interpreted in response to climate perturbations for frequency has been through the use of genesis indices. These are, at some level, they're heuristics. They can be more formalized and turned into actual statistical models that link the large-scale conditions that our experience tells us should drive, enhance, and reduce hurricane frequency, and connect them to large-scale environment to frequency. The experience of weather forecasters, dynamical understanding, et cetera, tell us that some large-scale conditions are favorable to the tropical cyclone genesis. These are weak vertical wind shear. Wind shear is the difference in wind speed with altitude in the atmosphere between, say, the surface and 15 kilometers of altitude or 10 kilometers of altitude. We also want high humidity in the free troposphere. This is useful for sustaining a hurricane as it entrains environmental air. We want large potential intensity. This is a theoretical upper bound on hurricane intensity. This tends to increase with warming. And then we want large background vorticity. This is sort of circulation, rotating circulation in the atmosphere, and large ascending motion in the atmosphere. We know qualitatively that all these things help tropical cyclone genesis. But as you can see here in these 3 illustrative examples below, these are genesis indices. These are actually equations that people developed to link these large-scale conditions to frequency. You end up having different formulations based upon what you assume and how you fit the data to the large-scale conditions. So, for example, this eta term over here in the Emmanuel index, it has a cube power to it, but in the Murakami and Wang index, it has a 3/2 power. And in the Tippett et al., it's actually part of an exponential linearly dependent in a Poisson regression model. And so you can see that these genesis indices don't even agree with each other on what the exponent should be on the data, and that's because they're put together sort of statistically or heuristically, and they don't really have a really deep dynamical basis. And not only that, but they assume something about tropical cyclones, that they essentially operate like a Poisson process. That is, that tropical cyclones spontaneously generate from a process where there are many trials and low probability of genesis in each one of them. And or alternatively, that climate impacts the probability of genesis, but not the trials, or that trials and odds have the same climate dependence. And that, you know, we know from our experience with weather forecasting and with exploring and watching tropical cyclones, is that none of the tropical cyclones don't spontaneously generate. All tropical cyclones that we see in observations come from a pre-existing disturbance that is different from a tropical cyclone. And so that these assumptions don't actually hold in our understanding. Not only that, these formulas that are fit to data fail to extrapolate to future climates. You can train them on a model and they don't predict the model's behavior in future states. So they don't help us understand the response in future climates. So what we've tried to do is move away from these genesis indices, or these specific genesis indices, and come up with something that is actually dynamically motivated. And what motivates what we've done is to work with a conceptual framework for TC genesis, in which you have a multi-stage process that leads to hurricane genesis, where you start out with weak rainfall clusters, or clusters that are relatively rainy, but they're weak circulation, that then develop into a rotating vortex, and then eventually, through different sets of processes, develop into a tropical cyclone. By splitting hurricane genesis into this multi-stage process, we can actually study the dynamics of each of the transitions. Instead of viewing as a tropical cyclone as something that is birthed and whole, we view it as something more like a frog, right? That starts out like an egg and then turns into a tadpole and then eventually turns into a frog. And at each of the life stages, it has different constraints. This is motivated in part because of analysis that shows that the energetics of the seeds, the things that precede tropical cyclones, and mature tropical cyclones are very different. This is a study led by Bozhong Zhang, where what you can see in the top is the contribution of evaporation. This is the classic feedback that drives tropical cyclones to the development of a tropical cyclone, and it's split based on intensity bins. Red indicates that a tropical cyclone is strengthened by evaporation. And what you can see is that mature tropical cyclones with a wind speed of 25 or 45 meters a second, have a very strong positive contribution from evaporation. However, weaker storms and the pre-existing storms, these things at 5 and 15 meters a second, in fact, are weakened by evaporation. They live differently. The precursors to tropical cyclones don't get their energy from evaporation. Rather, they get their energy from radiation, from convergence of light. This is largely infrared radiation. And so the precursors of tropical cyclones have a different energetic pathway. And so they're not just baby tropical cyclones, they are something else altogether that eventually develop into a tropical cyclone. Using this framework, Sung Lin-Hsieh was able to break down tropical cyclone genesis and its relationship to climate into a multi-stage process where seed genesis, these weakly rotating vortices, tend to depend on large-scale ascent and background rotation in the atmosphere. What you can see here is that the relationship across a range of climate states of predicted seeds to observed seeds, and you can see that this simple statistical model that is fundamentally you can trace it back to first principles physics, gives you a very good predictor. And then there was some dynamical understanding that was set by Brian Tang and Kerry Emanuel that developed this ventilation index, which is the ratio, it's a non-dimensional number that is the ratio of potential intensity, vertical wind shear, and moisture deficit. And this quantity has also a fundamental physical basis to understand the transition from a weakly rotating seed to a tropical cyclone. And when we combine these independent bases for developing a tropical cyclone, and we come up with the scaling that is informed by basic physics, we're able to come up with a statistical predictor that works across a broad range of climates to predict the actual change in TC frequency. And we can also show that seeds are not tropical cyclones. So now we have a tool that allows us to understand what controls tropical cyclone frequency. And unfortunately, it doesn't necessarily tell us which of the models is right, but now we have a tool that allows us to decompose what the response is controlled by. Now, what we really would like to do is use observations to help us constrain the response of tropical cyclone frequency in a warming climate. And as you can see in the left, we live in a planet that has been warming over the past century. These are global average temperatures. And in particular, over the last 40 years, temperatures have warmed by almost a degree Celsius. And so maybe we can use the behavior of tropical cyclones over the last 50 years to help constrain our expectations of the future. And so what you can see here is on the right, tropical cyclone frequency in the black line over the last 50 years. And in the red line is hurricane strength tropical cyclones. And you can see that there's been some modest changes, perhaps a slight decrease from 1970 to the present. And maybe this suggests that the models, this is over a period where the planet has warmed. So maybe this suggests that the models that give us a decrease in response to warming are giving us the right response. So what we can do is we have our global climate models. We have two versions, one that gives us a big increase in response to global warming and another that gives us a big decrease in response to global warming. And we can ask, in response to the observed ocean temperatures, do these two different models separate? Do they give us different historical estimates of what hurricane frequency should have done? And that's what's shown here on the right. This is a study led by Duo Chan, who's now at Southampton University as a professor. What we have in the left is observed hurricane frequency, that figure from the right, over this period where we've had about a degree of warming. And on the, on the left, on the right, we have two versions of the model. The red model is the one that in response to future warming gives us a big increase in hurricane frequency. And the black model is the version of the model that gives us in the future a big decrease in hurricane frequency. And I hope what you can see from that is over this satellite period, 1970 to the present, both of these models give very similar behavior. You do not see a separation between them to indicate that one of them has a bigger decrease and another one a bigger increase. And in particular, over the whole 20th century, when we have had a larger warming, you see that there is also no separation. So in spite of these models having very different response over the 21st century in their projections, they have pretty much the same response over the 20th century. And that creates a puzzle. Why do these two models that have very different responses in response to warming give very similar responses over a period where there has been warming? So one hypothesis we had was that the responses over the historical record are not dominated by the response to the mean warming that we've had, but rather the response to the patterns of temperature change that have existed over the historical record that may be different from the patterns of temperature change that we expect for the future. So we ran two versions of this model. One, this is the model that gives big increases in the 21st century. This is global frequency from 1870 to 2020. The red line shows the version of the model that is forced by ocean temperatures that have occurred over the 20th century and includes global warming. We can then rerun the model artificially removing historical global warming, but keeping the ocean temperature patterns that we've seen. And that's the blue line. And what you can see here is that, yes, in fact, historical hurricane frequency changes have been driven primarily by patterns of ocean temperature change, not by the mean warming. So the historical record does not serve as an adequate test of what the response of hurricane frequency to warming is. And so we cannot directly look at it to understand what we should expect in the future. This is also consistent with paleoclimatic analyses. This is some work by my colleagues Lizzie Wallace and Wencheng Yang, where we've looked at paleo tempestology reconstructions going back over the last millennium. And what you can see is that even though the past century has shown warming that stands out well above the historical or the prehistoric temperature changes on our planet, the hurricane frequency changes over the last millennium, the 20th century doesn't stand out. So we have been living through a period where ocean temperatures have behaved in a very unusual way. We've had a very clear warming of the planet, but the hurricane frequency changes have not yet separated from the background climate variability. Now, we still have our climate models telling us that we should expect changes in the future, although we don't know whether those should be for an increase or a decrease in hurricane frequency. And so my sense is that we're going to have to look at indirect estimates of which of these models is more correct. And here is one effort at that, where we use the El Nino Southern Oscillation Phenomenon, ENSO, or El Nino La Nina, and its response or its impact on hurricanes to try to distinguish which of these various models is most reliable or behaves more like observations. And what you should see here, these are the purple bar in all these is an observational estimate of what hurricanes should do in response to El Nino. And the blue, green, and red colored bars are the different models. Draw your attention to the red colored bar. That's the model that shows an increase in the future in response to warming. And in the various basins and globally, this is the model version that looks most like El Nino. So even though the consensus of climate models is that there should be, or like the majority of climate models say that you should expect a decrease in frequency in response to warming, the one model here that shows a very strong increase in the future is the one that looks best in response to El Nino. So the way I interpret this is that even though it's a minority vote, we should not dismiss this model that is telling us that we might expect warming in response to the future. Increase in hurricane frequency in response to future warming. And we need to better understand the dynamics of hurricanes. It's not going to, our reduction of uncertainty isn't going to come from just basically comparing frequency to frequency. Now I'm going to take a quick step to the side and look at major hurricanes. So far I've been talking about overall hurricane frequency. Those of you that study hurricane impacts are probably well aware that there's a disproportionate impact of hurricanes that are major. These are category 3, 4, 5, or hurricanes that have a sustained wind speeds of 50 meters seconds or larger. And that these hurricanes, although they represent a minority of the hurricanes, maybe 10% of hurricanes, are responsible for over 90% of losses. Here's a classic example. This is Hurricane Maria that had terrible impacts on life and ecosystems and property in Puerto Rico. And this is when the eye is over Puerto Rico. It was a major hurricane and it had massive impacts. So looking into the future, you look at these same models, and this is one result for which there's a lot of consistency across climate projections, which is that in response to future global warming, even though we're not sure what we expect hurricane frequency to do, overall hurricane frequency to do, there is a growing consensus that we expect major hurricanes with peak wind speeds of excess of 50 meters a second or 100 miles an hour to increase in a warming climate. Here are the results from a particular model. This is the model that shows increases in overall frequency in the 21st century. What's shown in these maps are the number of years, the change in the number of years with a major hurricane within 2.5 degrees of a point. 2.5 degrees is really representative of the scale of the core of the storm winds. So red areas and yellow areas are areas that are in increased threat in the future from major hurricanes. You should look at the panel on the right, because what that shows is changes in relative risk rather than absolute risk. And what you should see there is that there's a number of places in the Caribbean and the coastal United States where you get many 100% increases in the risk of major hurricane impacts in the 21st century. And it also includes these little black pixels there. Those are places where in the control climate, we don't have any major hurricane landfall, but in the future climate, we have major hurricanes impacting these areas. That is, you're going to have unprecedented impacts from major hurricanes according to this model projection. So can we look at the past to find support for these projections? Again, we've had about 1.5 degrees or 1.25 degrees of warming. Maybe we've seen an increase in major hurricane frequency. Well, it turns out this is an estimate of North Atlantic major hurricane frequency from 1850 to the present, low pass filtered. If you look at the raw major hurricane frequency counts, you see that there has been a recorded increase in hurricane frequency. However, we think that the recorded increase in major hurricane frequency in the Atlantic is largely related to changes in observing practices. And so when you adjust for missing storms, there's no real clear trend in hurricane frequency and major hurricane frequency. And the record is dominated by a deep gouge in the 1960s to the 2000s. You should see there, right, that there's about 3 major hurricanes per year in the North Atlantic, except in the 70s through 90s, it goes down to 1.5. So in spite of our models giving us a very clear projection of increasing Atlantic major hurricanes in the future, the historical record doesn't yet show that. So what's going on? Maybe our models are wrong. However, we can take these same models, these models that give us a major hurricane increase in the future, and we can ask what they do in response to the specific temperature changes that we've had over the last 100 years. And that's shown here in that orange line overlaid on the observed hurricane record. And you can see is that these models that are indicating that we should expect unprecedented major hurricane frequency in the current century also tell us that over the past century, we should have not yet seen a major hurricane increase. So it's telling us that what happened in the past and what's going to happen in the future are different. These models are also highlighting this deep gouge at the end of the record, this reduction of major hurricane frequency between 1960 to 1990, and an increase back up in the 2000s. And so we can ask ourselves, what is that deep gouge related to? You can then ask, is it due to the mean warming? Any of this due to the mean warming? And in fact, no, this model again is telling us that major hurricane frequency changes in the Atlantic are largely the response to patterns of temperature change, not to the mean warming yet, although future major hurricane frequency changes are going to be dominated by the response to mean warming. What is driving that big decrease in hurricanes at the end of the 20th century? Well, on the left, this is one of the leading contenders for explaining that. You see European sulfate emissions that grow very rapidly after World War II, following the big industrial buildup, and then decrease as clean air regulations are put in place in the 1970s and 1980s. This sulfate emission, part of it blew out into the North Atlantic and caused relative cooling of the North Atlantic. And so if you look at climate models, these are estimates of changes in hurricane intensity over the Atlantic over the 20th century. The black line shows what our climate models tell us should have happened in response to all forcings. That includes aerosols and greenhouse gases. Oh, sorry. Whoops. That includes aerosols and greenhouse gases. You see that the deep gouge comes out there. The models in response to greenhouse gases alone in the red line there say that if we had only had greenhouse gas changes over the 20th century, we should have had an increase in major hurricane frequency or hurricane activity. But that was offset by the aerosol effect. And so what we're living through right now is a period in which greenhouse gas induced intensification of Atlantic hurricanes has been hidden from us by these aerosol changes. These aerosol changes are now being removed. And so global warming is being unmasked, or rather the impact of global warming on hurricanes is being unmasked. And over the coming century, we're going to see a growing dominance of greenhouse gas impacts. Now, this is only an Atlantic story. If you look at the rest of the world, we should already be seeing an impact of hurricane intensification from the warming. However, we don't have high quality data records outside of the Atlantic to span the century. So I think this calls for us to try to reconstruct hurricane activity in other basins so that we can actually better see what we expect in other basins. So a summary of what was shown so far. Historical multidecadal global TC frequencies do not constrain future sensitivity to warming. We're going to need indirect constraints on hurricane frequency. The historical global decrease of hurricane frequency has been driven by patterns of ocean temperature change. These past ocean temperature change patterns are very peculiar. They do not look like what our climate models say we should have gotten. And so a question remains, are they forced by radiative forcing, or are they due to internal climate variability? In addition, historical major hurricane frequency should have given us an increase globally, although we do not have the data to actually see it. In the Atlantic, we should not expect a clear trend, largely due to aerosol masking. But in the future, we should expect an intensification of Atlantic hurricanes and globally. And really, this requires us to have indirect constraints on hurricane activity so that we can really test our models. We're not going to be able to test them directly. It would be great to develop West Pacific proxy hurricane data, better understand El Nino, and develop better understanding. I think I've come to my limit, but I did want to point out a couple of things where we do have really, having highlighted a bit of uncertainty about the impacts of global warming on hurricanes, I really want to point out some things where we do have really strong confidence. In addition to the intensification of hurricanes, we have really strong confidence that we should expect a superclassus clapeyron, that is a greater than 7% per degree increase in tropical cyclone rainfall. That urbanization should impact the response or how human beings experience hurricane changes, and that both ocean warming and land ice melt, we know with almost absolute confidence, will raise sea level. So even if hurricane frequency doesn't change, their storm surge will be more impactful. So there's a lot of things that we do understand about the impacts of tropical cyclones and how they impact humanity. Although, as I said here, some questions still remain. And I think I'm very confident that over the next few years, by focusing on understanding and bringing new people and new ideas into this, we'll be able to improve our understanding. With that, thank you.
Thank you, Gabe, for this very, very extremely interesting seminar. And so I think that there's room for some questions. So we take questions, both from the audience here and online. I see already some hand here.
Hi, Gabe. This is Simona. Very nice seeing you. So I have one question regarding the importance of the SST patterns associated with El Nino, La Nina. This is where CIMMYT models, when you look at the historical simulations, they really differ from observations, right? The observations tell us that there is a trend that would correspond to a La Nina pattern, whereas most models give us the opposite trend. And so I was wondering if that is one way to maybe start looking at possible differences or discrepancies between both observed trends and future trends.
So Simona, first off, hi, and I can't wait to see you in person again soon. But it is, I think you've hit on something that is a really crucial topic, not just for understanding hurricane frequency, but also for understanding climate sensitivity, the response of rainfall and drought. We have a big discrepancy between what our climate models are telling us the tropical Pacific should have done and what we think the tropical Pacific did do. I think we need to, number one, make that clear to the world so that they understand what is going on. And number two, we need to work to reconcile that. Currently, I think there's some very good ideas out there on how to do that, but I think that we do need to work more on that question.
Okay, then there is another question from the room. Panos there. Yeah.
Yes, I formulated my question during the talk, and I submitted it online. I think you have already answered what I asked. I was asking, first of all, whether the impacts of changing aerosol concentrations may be competing with the impacts from greenhouse gas concentrations, and you already answered this. And whether you will say in a sentence whether the warming oceans matter more than the changing atmosphere, and you also answered this. So I would only like to mention that at CMCC we have run a set of simulations with that contribute to the large ensemble single forcing MIP, where we run historical simulations changing a single forcing only. And I think it will be interesting to see if we track TCs in these simulations, what are the different impacts. Any further comments, very, very welcome, of course.
So I think that you are those single forcing experiments would be wonderful to look into, and I think a great opportunity to better understand. You know, the response to aerosols is coming out as one of these confounding factors that complicates the interpretation of the 20th century. And it's also one of the things that we understand the least in the climate system, right? CO2 is complicated, but a molecule of CO2 is a molecule of CO2, right? There's not a lot of variety there. And so we can really understand it at a very fundamental level. Aerosols are intrinsically complex, right? It matters whether you're dealing with sulfate or whether you're dealing with black carbon or whether the black carbon and the sulfate aggregate. It matters whether they're occurring in a place where you have high cold clouds or whether you have warm clouds. The aerosol cloud interaction is different. And so the conclusion that aerosols help explain the 20th century, to me, is a temporary answer, because I am less confident in that than I am in many other things. And so I think it would be a wonderful thing to look at these single forcing experiments. And then what I would love to think about is, are there idealized aerosol experiments that could help us better understand the emergent behavior of aerosols? Because everything is hyper realistic or hyper comprehensive, and I have a real hard time understanding what happens and why.
Okay, still one question from the room. So Soleil, here.
Hello, it's Sohail. Nice to meet you. So I wanted to ask, continue about this discussion of aerosols, because also there are lots of interest in terms of future applications of solar radiative management using aerosol for cooling. And usually also we are looking at historical implications of volcanoes for that. Do you think looking at historical volcanoes eruptions can help explain some of the changes you see also in the major hurricane frequencies?
So this is a great question, and I'd love to unpack all the layers, the solar geoengineering piece and the volcano piece. I'll start with the volcano piece. I think that there's sort of substantial room for volcanoes impacting the historical hurricane frequency record. However, work that we've done here, if you just send me an email, I can point you to a paper of my colleague Wenchang Yang, who was able to show that the meridional structure of the volcanic ash plume in the stratosphere, whether it is primarily in the northern hemisphere, like Santa Maria volcano was, or whether it's primarily in the southern hemisphere, like Agung was, or where there's a symmetric about the equator, like Pinatubo was, changes the response of rainfall and hurricanes to different volcanoes. So it's a very complex thing to understand, but I think it's a very important one. Now, with regards to the geoengineering question, I think that this meridional structure thing that I've mentioned also plays a role. If you start thinking about the response of hurricanes to deliberate application of aerosols in the stratosphere, the meridional structure of the forcing will matter and could have very large effects that are disproportionate to the effects of the overall warming. And so it's in assessing the pluses and minuses of geoengineering, we really need to look at our ability to control the meridional structure of this geoengineering.
Okay, there are also a few questions from people online, and so I'm going to read it. So the first one is from Lucy from Brazil, and great talk. Are there studies that separately evaluate expected patterns in the northern and southern hemisphere? If so, how similar, different are they?
So this is a great question, Lucy. There are, and they are very different. So each basin responds differently in practically every study. One of the things that we tend to see in many models is a northward shift of hurricane activity in response to warming, but that's not in every study. So there are some studies, and also the response to aerosols has a very big north-south asymmetry because aerosols primarily have gone in the northern hemisphere, at least anthropogenic ones. And so you expect sort of a north-south asymmetry there. There's a very nice paper came out a few months ago by Hiro Murakami talking about all the regional responses to historical aerosols in different hurricane basins.
Okay, another question from people online. There's sorry for the misspelling of the name, sorry, Ashwini Otta. And the question is, given the uncertainties with frequency, is it prudent from engineering decision-making that we assume the future frequency is same as historical?
So that's a very good question. I think it will, the answer to that question will depend on the application. I think that the uncertainty to me points to any engineering decision that needs to be made now should be made robust to both increases and decreases. And if there's asymmetric cost functions, right? If the penalty to whatever you're designing of having more hurricanes is greater than the penalty for incorrectly, getting too few, then you're going to. So I think there needs to be an asymmetry in the design. Uncertainty. We're going to have to design in a world of really deep uncertainty. So I wouldn't necessarily assume that things are going to be the same. I think this calls for studying the sensitivity and better understanding where the gaps in resilience are. Yeah.
Okay, then Paolo Scussolini, models Hiram and AM 2.5 go well in step in yielding TC until about the 80s, with similar high frequency variability, but they seem to diverge later. Is there any explanation? There's
a great question. I'm sure there's an explanation. We're trying to dig into it and figure out what the explanation is, but I don't have one yet for you. These are like all models and all model experiments. These are insufficiently analyzed. This is one of the things that I'm very excited about our collaboration between CMCC and HMEI is that to bring more hands on deck, have some Princeton people working with CMCC scientists to better understand the studies we have and what we know and we don't know. Good eye there.
Okay, now a question from Rachel Jonathan. Oh, it has disappeared. Okay. With regard to the aerosol impacts, would we not expect strong aerosol impacts extending into future from industrial activity in India and China, impacting respectively activity in the Indian Ocean and Western Pacific?
So that is very perceptive and correct, Rachel. So there's already evidence that in the historical record, the buildup of different types of aerosols, both in South Asia and East Asia, has impacted cyclones in the Indian Ocean and in the West Pacific. And it's done so with different rhythms, and because each of the basins has its own character. The response to aerosols isn't always the same. But I will point, there is this study by Hiro Murakami this year and another one 2 years ago that goes into some detail explaining it.
Okay, so there are two more questions. Do you have time, Gabe, for?
Absolutely.
Okay, great. So Branko Grisogono asks, would you highlight the importance of air-sea interaction for TC initialization, development, duration, and eventual dissipations? Models seem to treat this interaction inadequately in terms of wind current stress, roughness, spatiotemporal changes, and more.
So I think, yeah, Branko, there is a variety of aspects of the air-sea interaction that seem important to tropical cyclone at different scales. Everything from sea spray generation as breaking waves. That sea spray, those droplets of air in the atmosphere, once you get sort of very strong waves, increase the effective evaporation rate under hurricanes and can act to amplify them. Simultaneously, as wind waves generate and then break and you start losing the structure of the surface of the ocean, the roughness of the ocean and the momentum drag coefficient for cyclones weakens, and so you can have this other amplifying effect from, this is all small scale, say on the scale of meters and less than a kilometer. But then when you go to larger scales, there are feedbacks as a hurricane goes by. If the mixed layer depth is very low, very shallow, and you have cold water available below, a hurricane may cool the surface and essentially kill itself off. And so there is evidence that the three-dimensional structure of temperature and salinity in the ocean is a key constraint to hurricane intensification. And then also more recently, there's some work showing that these episodic, what are they called, ocean heat waves or marine heat waves, can have an effect on tropical cyclone genesis and steering and intensification. And these are all, I think, represented at different levels of say realism within models. And I think as we learn more, there's a lot more to be done. And so I think there's a lot of potential for some really cool fluid dynamics across a number of scales in air-sea interaction work.
Okay, so now the last question from online attendees, Giovanni Liguori. And the question is, the major source of aerosol have shifted over time, with North America previously being a dominant contributor, whereas Asia is now a more significant source. Could this temporal change have influenced the observed trends, and might similar shifts play a role in the future in the regions with major sources change again?
So I think Giovanni hits on a key thing. So aerosols can change very rapidly. They have a very short lifetime in the atmosphere, a lifetime of days and weeks, and human decisions and actions can also change aerosol concentrations also very rapidly. You turn on a power plant, you turn off a power plant, you have almost immediate impacts. And so we've seen this as first Europe and the United States were the dominant aerosol emitters. Then now you have more industrialization happening in East Asia and South Asia. And there's also been some indications that East Asian aerosols have been starting to come down as people, and this is on the last few years since the Olympics essentially in Beijing. And so you have these really high frequency changes in aerosols that are very spatially heterogeneous. And since they've happened so rapidly over my lifetime, I have no reason to think that similar changes won't happen in the future, right? And so these decisions, these human decisions and the impacts of these decisions, including, by the way, the recent switch in maritime fuel, many of you may be aware of, there was this switch in 2020 for marine fuel to be a lot cleaner, fewer sulfates, also it may have impacted tropical cyclones by changing sort of the patterns of aerosol distribution at sea. And then there's also the natural aerosol sources, the dust from the Sahara and the dust from the Gobi that also could impact. And so this aerosol question is one that should leave us with a sense that even though we should have a very clear expectation that greenhouse gases should give us more intense, wetter, and more impactful surge from cyclones, on top of that are going to be these other anthropogenic and natural drivers, including internal climate variability, that are going to give us a rich spectrum in space and in time. And we as a community need to be up to the task of providing society with the type of information that is going to be needed to make decisions. And so we really need to deepen our understanding. We need to work together to design experiments and forecast systems that are relevant. And given the really big steps forward that we've made in understanding in the last 20 years, I think I'm hopeful for it in the future. So.
Okay, so if there are no other questions from the audience, I abuse of my power as moderator and I ask the very last one. Then we stop. Gabe, you didn't use one single time the wording artificial intelligence or machine learning. And at the same time, if I got it right, you mentioned it several times that what we see has happened in the past to these things is probably different from what we should expect in the future. So does it mean that we cannot rely on machine learning methodologies to explore this kind of problems?
So I think I would be, I'll start by saying I don't think that I know we can't rely on machine learning. In fact, every time that I work with machine learning, I am surprised by how it's able, done right with a certain amount of skepticism as you develop it. It's able to do things that intuitively I felt it wasn't able to do or wouldn't have been able to do. However, given this separation between what has been dominant in the past and what might be important in the future, I think we need to be very judicious about how we use artificial intelligence. Artificial intelligence and the results from it are very seductive. And so we need to work with them, with these methods, to really figure out which of these methods are applicable in a changing climate, in a world where we have insufficient past information. And I don't think that, or how should I say it? I'll say it positively. I do think that AI and machine learning will be an important element of our tools going forward. But I don't think that they will be best used in isolation. They need to be used in a larger universe where dynamical understanding underpins how we interpret things, where we invest in sort of improving our observations and our dynamical modeling techniques, where we work into hybrid dynamical statistical systems where the statistical system is AI machine learning. And so I think there's a lot of hope and a lot of potential there, but I don't think that it's going to come out of the box. And so I think the successes that we've seen in weather forecasting from machine learning and AI, and they have been successes, they're very impressive, aren't going to translate literally to the climate change application, but they should serve as motivation to figure out how we can use these great technologies in this application.